Okay, can I start?
Now it works great.
Perfect. Thank you very much.
No,
Please
thank you
start.
to you for the introduction. Good morning or good evening, everybody. I'm Dalila Grilli. I would apologize for my lover, which is Peter Barrett, but for it is for a problem of link connection. And I am a geologist, and I've been working in E&I since 2018. I started my career as a petrophysicist, and then in 2020 I moved to the geomechanical department. And today I would like to present to you the work about an algorithm for stress inversion based on a borehole image data and further application to a carbonate framework. This work was developed in collaboration with my colleagues Stefania Petroselli, who is an engineer from Geomechanical department, and Alberto Vercellino from the Petrophysical department. This is the agenda for today's presentation. I'll start with a brief introduction regarding the importance of understanding the stress condition, considering the outputs from image log. And then I'll move to the explanation about the stress inversion workflow internally developed and consequent application of this stress inversion workflow to a real case study on a carbonate reservoir. And then I'll go through some conclusions considering all the discussions behind. First of all, just a little introduction about the motivation for which we decided to develop this kind of workflow. Determining the stress magnitude can be fundamental for a wide range of analysis, also for safety and environment issue, such as, for example, wearable stability and some risk linked to the production, such as standard risk evaluation and further issues linked to the reservoir scale, such as compaction and subsidence. But the image log can provide image logs can provide important information about the direction of the minimum and the maximum horizontal stress, but not the magnitude. And for this reason, we decided to take the information from image logs and put them into a proper developed workflow to determine the stress magnitude starting from the image log outputs. But how the stress inversion workflow works? You can find a brief overview in this slide. Starting from the inputs needed to for the workflow, we can start with for sure the true vertical depth subsea, and then as I said in the introduction, the image log outputs, such as information about breakouts as azimuth and width, and the minimum horizontal stress azimuth, considering the main features from the image log outputs, induced fractures and breakouts. Then some information about standard logs, such as porosity, bulk density, and then drilling information, such as mud density. And regarding the geomechanical inputs, we have the elastic moduli, which can be from both lab test and log computation, and failure criterion to apply to the workflow. We implemented Moore-Coulomb, Galileo, Tresca, and Oke-Brown failure criterion. Then the all these inputs are put into a MATLAB code, which is able to perform a pre-processing and then a stress evaluation. We can go, I'll go through in detail on this in these main steps in the next slides, but just to provide you a overall view. I see that in the post-processing, the script computes the main parameters such as the vertical effective stress, the bed pressure and formation pressure, and minimum stress horizontally and radially. Considering the borehole. And then all the input and the preprocessing parameters are inserted into the stress evaluation, which accounts for tensile failure and compressive failure. And it applies a maximum horizontal stress from the inversion model. Looking in detail into the main input data, the information about the tensile failure are expressed in terms of flag, which is set into to 1 if the tensile failure are present, or to 0 if they are not present. And then once we observe, for example, the tensile failure, we set the inclination of the azimuth of these features and the minimum effective stress considering this feature. The same it's for the compressive failure, which are expressed in terms of flag for the presence or not, the azimuth, and in addition to this information, we set also the breakout width. Then another family of input data for this computation is the formation and the mud properties. As I said in introduction, the porosity, the bulk density, the mud density, the formation pressure, and the interval depth of the analysis. For example, we observe tensile failure in a certain depth, certain interval, and then set this interval for the analysis. And then the elastic moduli for the inversion model, which are Young modulus and Poisson ratio. Looking in detail into the pre-processing part of the script, starting from the input data, we can perform some computation to determine input parameters for the stress inversion model. In particular, the bulk density, so the density of the formation, and the formation pressure are fundamental to obtain the total and effective vertical stress. In particular, the integral of bulk density versus the true vertical depth provides the total vertical stress. And then by subtracting the formation pressure from this quantity, we obtain also the effective vertical stress. With the same philosophy, we can compute the mud pressure from mud density and depth, and by subtracting the formation pressure, we obtain the net pressure. And finally, considering the mud pressure, the formation pressure, and the minimum effective stress from, for example, frag test, we obtain the horizontal minimum effective stress and the radial effective stress. All these computation are made consequently. All these quantities are fundamental to determine the range of the maximum horizontal stress. How can we compute this? In particular, first of all, we we choose the failure criterion. In this script, we implemented 4 failure criterions, which are more Coulomb, which is the most conservative, Galileo, Tresca, and Oke-Brown, which is a generalization of more Coulomb criterion. Then we compare the computed horizontal stress with the information about tensile compressive failure. In particular, if there are no tensile compressive failure, the computed horizontal stress is an upper limit. On the contrary, the computed horizontal stress would be the lower limit. So just to stress all the information provided in these slides, we can see that the proposed workflow provides a range of maximum horizontal stress, considering both information from the well and information from theoretical computation. Now we can pass to the application of this workflow on a real case study, which is an offshore well drilled in a carbonate reservoir characterized by a good porosity enhanced by open fractures. In this well, we acquired image log, which highlights both resistive and conductive fractures. And then we applied the stress inversion workflow to determine the stress regime, comparing also the information from other logs. Just a brief overview of the well. As I said, the reservoir is a carbonate reservoir with a ceiling composed by a salt subsection and a marl ceiling, and the mud used to drill this well was a water-based mud, and the main phase which drilled the reservoir was 12 and quarter and 8 and half. And in this session, we acquired LWD triple combo for the formation evaluation, the classical formation evaluation, standard formation evaluation, the Wehrlein macroresistivity formation images, and the Wehrlein dipole sonic log, which provided important information regarding the anisotropy and open fractures. The image log peaking provided important information regarding the nature of the fractures and the stress regime. In particular, we classified the dips as bedding, for sure, which are present in our formation, and both natural and induced fractures. The induced fractures, we can just sorry, okay. The induced fractures are the main inputs for our stress inversion workflow, which provides important information about the orientation of the horizontal stress. And then we have a different set of natural fractures, both resistive and conductive, and then also shear and joints, providing a particular framework of the reservoir. Considering the main reservoir part, we identified 4 fractured zones, and in particular we were interested in determine these mega events in red, which were important to determine their contribution to the production, for example. And then there were also faults and some minor events which can be detected by the image logs, which were important also to enhance the permeability and the porosity. The information from image log, just to have a look on the importance of this analysis on, for example, the production, were upscaled. The results from image logs were upscaled to propagate the information about the enhancement of the matrix in terms of dissolution and natural fractures to the model. In particular, the reservoir geologist built two kind of boxes to represent the enhancement of the porosity in the matrix in terms of dissolution, and about the natural fracture was built a cylinder to consider also this kind of feature. All of this information from image logs propagated to the model provided important information both for the production optimization and for the understanding of, for example, water cut. All these results from image log were compared also with other information from sonic logs. In particular, the conductive fractures were in correspondence of chevron patterns from stone lay processing. This was another confirmation about the fact that the fractures were open. Whereas in the part of resistive fractures, the chevron patterns were not present. Another important information could be from the dispersion plot from dipole processing. In particular, as you can see in this plot, we observed intrinsic anisotropy at formation scale. In fact, the fast and slow shear are different. But in this plot, and this anisotropy could be related to the fracture. But this plot can provide us another important information. In fact, in the near wellbore, the fast and slow shear crossed, and this is a particular feature that is linked to the anisotropy driven by the stress. So we can say that the fast shear azimuth from sonic anisotropy analysis can be also an indication of the direction of the maximum horizontal stress. In fact, we compared the information from the stress inversion workflow performed on this well with the information from both sonic and image logs. In particular, in this track, in black line, we plotted the fascial azimuth, and the black dots are the information, the stress, the maximum horizontal stress from stress inversion workflow. And as you can see, there is a good match between the two analyses. And furthermore, also we consider the maximum horizontal stress from log analysis, which involves different logs such as density, sonic, and pore pressure from operative analysis. And as you can see, the computation of maximum horizontal stress fits well with the minimum of the maximum horizontal stress from the stress inversion workflow. The other limits is in red, represented by these two red dots. So we can conclude that in this well, we had important information from image logs, both for production and stress regime. But also the sonic logs provided us important information about the anisotropy and the fracture aperture. So we compared all this information with our stress inversion workflow to determine important features not only for the wearable stability and analysis in which geomechanical inputs are important, but also for the production and the operations in general. So just to sum up what I showed you in these slides, we can see that the proposed workflow was developed in order to obtain information regarding the range of the maximum horizontal stress, which is important for a wide range of analysis, also in terms of health and safety, such as wellbore stability, subsidence, and so on. And to show you the possible application of this workflow, I showed a real case study with the stress regime can had a strong impact on fracture aperture, and then for on the permeability enhancement. So we can conclude that the stress inversion procedure represents a very useful tool for all disciplines in which the geomechanical analysis are involved. And it is easy to use since it involves some inputs that you can easily obtain from image log and from drilling parameters. Furthermore, the fact that the MATLAB coding was developed internally is easy to manage in case of changing, and we can tailor the workflow on our needs. We are planning in the future to integrate this script in a commercial software to make it more user-friendly, and then to continue the analysis on the real case study on other wells. Finally, I would like to thank the other authors for sure, and all the ENI team who collaborated for the stress inversion workflow development. And I leave here some references which are useful to go in deep with this feature. Thank you.
Great. Thank you, Dalila. We have a question from Motaba Rajabi who says, great presentation. How does your method differ from the 1D mechanical Earth model commonly used in the petroleum industry? Thank you.
Thank you for the question. Okay, usually the 1D mechanical Earth model is based on log continuously, and it involves, for example, dynamic parameter, and it provides a profile of the stress, but in this case we but it not it doesn't take into account the information from image log, which are very important for to assess the reliability of the analysis. And this workflow can consider also this information in the evaluation. So the importance of this workflow is linked to the integration of both information from other logs and image logs, which is new to the standard 1D mechanical Earth model.
Thank you. Do we have any other questions?
Okay, nice.
Yeah, Brice, do you want to ask your question?
Yeah, sure. It was a very good presentation. Thanks a lot.
Thank you to you.
I wonder, do you manage to run the workflow for supporting drilling or completion operation, or is it something you use as a post-well analysis or for field development?
At the moment, since it is a new workflow, we have used it only for a post-drilling operation, but it can be a useful tool also for real-time analysis for sure,
Okay.
because it
Thanks,
is
great.
very. Oh, thank you. Nice to hear you.
Thank you. Do we have any other questions?
Yeah, this is Saeed Ahmed from Pakistan. I have one question. First of all, it was very nice presentation, and it's a good work shared by Peter. And there's one question related to is your model works very well in a compressional or in an extensional environment, because at this time we have drilled so many wells in the compressional environment, but our model didn't work in the compressional environment. Sometimes it works in a extensional environment, but we do see the problems in the compressional environment. Thank you.
Oh, thank you to you. Okay. Yeah, it works well in the compression environment, but the workflow considers also the possibility to have another stress regime, not the normal not only the stress regime. So it is very useful and applicable to a wide range of environment, both in normal and not normal stress conditions. So we tried this in other situation, and it works well, providing important information also to support, for example, the operation.
Yeah, hi, this is Bastian Rothers from Nimburg Geoscience. I just have a probably silly question because I'm not a structural geologist. You
No.
said that you use as a input parameter the TVD subsea. So what would happen if you have an well, let's say, at an altitude of 1 kilometer? Because I mean, then you would lose quite a number of vertical.
So didn't get probably the question. Do you mean in an onshore well,
Yes,
for
so
example?
at a
Okay,
high altitude.
yeah. No. In onshore well, we also consider, for example, you have no problem instead, but because you consider also the mass rock on your reservoir. You consider the true vertical subsea because it's important also to consider, for example, in offshore well, the
Yeah.
weight of the water. But in onshore well is the same thing if you think about, but you have the mass rock, sorry, instead of the water. So it's the same.
Okay, thank you.
Thank you to you.
Okay, thank you. Thank you very much, Dalila. Great presentation. Our next talk is from Dalia Grilli with ENI, and it's going to be on an algorithm for stress inversion based on borehole image data, application to Carbonate Framework. So,
Yeah.